Our first example here is a meter stick, which is balancing on some kind of fulcrum, which is the triangle over here. And it is, as we know, the length is going to be 1 meter. It has a 50-gram mass, a 75-gram mass, and a 150-gram mass. Or sorry, the meter stick is 150 grams. And we want to find the mass of M3 and the normal force being applied by the fulcrum. So, as we know, we're given distances and we're given mass, which can be translated to weight, which is a force. So this is a pretty good indication that we're looking at a torque problem. Okay, so I will transfer this over to the whiteboard and we can get started. Okay, so as we know from the problem, we are given a meter stick with a mass M1 at one end, M2 a little further in. It's got a fulcrum and a third mass at the other end. And we know that there's 30 centimeters between M1 and M2, 40 centimeters between M2 and the fulcrum, and another 30 centimeters between the fulcrum and M3. And we also know that the meter stick itself weighs 150 grams. M1 is 50 grams. M2 is 75 grams. And M3 we are trying to solve for. So Bhavdeep, knowing that we're looking at forces here and that we're trying to solve for missing forces and masses, what would be the first step in this problem, do you think?
Well, I think that since we have most of the quantities in the figure, and since we're just trying to find one, I mean, there's just one unknown in this case, we could possibly try solving for the torque. And well, since we know that the entire thing is in equilibrium, we could figure out that the sum of all torques, or the summation of all summation of tau is equal to 0. We could rearrange that into an equation and try to find for the unknown.
Exactly. So as you said, we do know most of the values in this, and we know that it's a static equilibrium problem, which tells us that the sum of forces in the x direction, the sum of forces in the y direction, and the sum of torques is going to be equal to 0. This is just given information about any static equilibrium problem. And as you said, we're going to start with the sum of torques equation, as we have a lot of information about the problem, and this will be the easiest to solve for. But first, to make it easier for me to identify which forces are acting on the object and which are applying a torque, I'm going to start with a free body diagram. So I'm going to have this line be the meter stick. And I'm going to have M1G on the left side, as we know it is just going to be the weight of the object. I'm going to have M2G. I know that this one will be M3G at the end. The fulcrum must be pushing up with some kind of normal force. So I'm just going to call that N for normal force. And I know that in the middle of the meter stick, as the meter stick does have mass, it will also have a weight, and I'm just going to call that mg. So I'm going to refer to that 150 gram mass as m. So those are all of the forces acting on this meter stick. And we're going to start with the sum of torques equation. So torque, as we know, is equal to radius cross force. So we're looking at the radius from a point that I'm going to choose, and seeing as I don't know what this normal force is, I'm going to choose the placement of the fulcrum to be the point from which I measure my radius. I'm going to call that 0. That way, when I'm multiplying the normal force times a radius of 0, I get a torque of 0. So I don't have to worry about what the value of the normal force is yet. So that eliminates a value that I don't know, which will leave me with 4 forces that will now apply a torque. So setting up my equation, I have m3g times my distance, and I know that that is 30 centimeters from the fulcrum. And is that positive or negative, Bhavdeep?
Well, this should be negative primarily because it's, I mean, if it does rotate, it's going to rotate in a clockwise direction. Convention says that we should take it as negative.
Exactly. So in this situation, you can use your right-hand rule and determine that, or you can just look at the problem and see that if I have an object that is pinned at this point here, my 0 point, and is being pushed on the right side, it is likely to rotate in a clockwise direction, which is considered negative. So using that concept, I now have my next force, which is mg. And where should the weight of the meter stick be placed, Bhavdeep?
It should be placed at the center of gravity, which should technically coincide with the center of mass.
Okay, exactly. So if I know that my fulcrum over here is 70 centimeters from the end of the meter stick, and my center of mass, which is somewhere around here, should be 50 centimeters, that leaves me with a distance of 20 centimeters from the fulcrum to the center of mass. And I know that this will be in a counterclockwise direction, so that is positive. And the same will be true of the next couple of forces. So I have m1g, which is located at 70 centimeters away. And I have m2g, which is located at 40 centimeters. And all of these distances are just being taken from the drawing above, which shows me the distance of each force from the fulcrum. So I've taken the torque of all 4 of my forces that apply. And when I take the sum of all of those, I know that it is equal to 0. Now I have a value for m, and g is obviously known as a constant. I have a value of m1, I have a value of m2, which is leaving me with m3 only as my only unknown in this problem. And that is what I'm trying to solve for, so that means that this is going to be a good way to solve for it. So I'm going to clear the whiteboard to give me a little bit more space to work, and I will finish this problem. So the sum of all of the torques is equal to 150 times 20 centimeters plus 50 times g. I'm just going to leave that as g, but we know that that is 9.80 times 70 centimeters plus 75 times g times 40 centimeters minus m3, which is still unknown, times g times 30 centimeters. And this is all equal to 0. So using my algebra, rearranging and solving for m3, I get a value of 317 grams. And that is the answer to part A of this problem. That is the mass of the third mass on the meter stick. And the way we solved for this was using our concept of static equilibrium. Do you have anything to add to this, Bhavdeep?
Nothing particular. Just keep in mind where, as we mentioned earlier, just either use your right hand rule, or kind of just assume or make sure that you're taking the sign convention correctly as to where the object or the scale in this case would have the potential to rotate. If you don't do that, then you might get a negative answer, which negative mass doesn't really make sense. So just make sure of your sign conventions.
Mm-hmm. It's a very good point. And just dealing with torque in general, some of the most important things are to watch your sign convention counterclockwise and clockwise. to make sure you pay attention to where you're measuring your radius from, because it has to be consistently from the same point, and to make sure that you're only taking the value of the force that is perpendicular to the object. So in this case, because the masses were hanging straight down, all of the mass was perpendicular, but that is not always the case. So making sure to pay attention to that. But we're going to move on to part B of this problem, which is asking for the normal force. So I'm going to clear this. So again, we have our object. We have 50 grams on the first mass, 75 grams on the second. We now solved for 317 grams for the third. We know that the fulcrum is here and that the object itself is 150 grams. The meter stick is 150 grams. We also know that the distance here is 30 centimeters, 40 centimeters, and then 30 centimeters. And that there is a normal force being provided by the fulcrum here. So again, we're putting that information down because this is how we're going to solve for our problem. We started with 3 equations because it's in static equilibrium. So we know that the sum of the torques is equal to 0. The sum of the forces in X is equal to 0. And the sum of the forces in Y is equal to 0. And now I'm trying to find what the normal force is equal to. So normal force is equal to what? And I know that because it's a static equilibrium problem, that I'm going to need to use one of these equations. I just have to decide on which one. So there don't seem to be any forces in the X direction, so automatically I'm going to remove the sum of forces in the X. And we just did a torque problem, so chances are I'm not going to want to use that again right away, which leaves me with the sum of forces in the Y direction. And when I'm looking at the sum of forces in the Y direction, Bhavdeep, does it matter what distance apart they are, or does it just matter which direction they're pointing in?
It doesn't matter what distance they are at. It just matters the direction that they're pointing in. The distance will matter if it was torque, but the force barely depends upon the distance. So we should be good.
Okay. Yeah, so torque is the only kind of problem where you're going to have to worry about distance. In this case, we're just looking at our sign convention, and I'm going to say that up is positive and down is negative. I want to be consistent with this. So if I put my sum of forces in the Y, I have my normal force, which is pointing upwards, and the rest of my forces are pointing down. And because I'm solving for a force, which is in newtons, which would be kilograms times meter squared per second squared, or kilograms times meter per second squared, I am going to convert my masses to kilograms now. So I'm going to say 0.050 kilograms. And that is times G, which I'm just going to leave as a constant, but we know the value of that. And I'm going to subtract again. We have 0.075 kilograms, so that's mass 2, times G, and minus 0.317 kilograms, again times G. And there's one more that I actually forgot to put on this free body diagram, but that is the mass of the meter stick, and that is 0.150 kilograms times G. It is important to keep the units consistent. We know that our gravity value is in meters per second squared. We know that our Newton has kilograms in it, so I have converted the units. It wasn't a problem in the last problem because we were solving for mass, so we were going to get grams anyway. But when you're solving for forces, you tend to want to check your units. So again, this is all equal to 0. So I have all of the values except for my normal force. And again, I use my algebra to rearrange and solve for the normal, which gives me a normal force of 5.8 newtons. And that is the final answer for part B. So we did a very similar process to step 1, where we used our static equilibrium concept. We added up the sum of all of our forces, set it equal to 0, and rearranged to solve for our variable. And as you can see, we couldn't do part B without solving for part A, as we needed mass 3.
So the second problem talks a little bit more about equilibrium. It talks about mountain climbing. And I don't know, seeing as the new Spartan Recreation Center opened up, I guess this was a nice question to kind of just throw in. So mountaineers often tend to, well, get off mountains using this process called rappelling. Anybody who plays Rainbow Six Siege knows about this. We do this a lot. Anyway, so we have a mountaineer who's 82 kilograms, and he's 1.9 meters tall and has a center of gravity 1.1 meters from his feet. He rappels down a vertical cliff with his body raised at a 35-degree angle. He holds a rope 1.40 meters from his feet and makes a 25-degree angle with the cliff as well. So we got two angles in there. So we need to find the tension that the rope needs to support, and we need to find the horizontal and the vertical components of the um, force that the climber's face exerts on the climber's feet. So essentially, the force along the climber's body, and we need to find the minimum coefficient of static friction that is required to prevent the climber's feet from slipping. Well, if the climber slips, then he dies, so we kind of have to save the climber in this case. If there's any questions, I mean, that's pretty much the question. So given a practical application, we need to find out, well, practical application of equilibrium, we need to find out certain quantities. If there are any questions, now is the time, so we could move on to the whiteboard and start solving for the required quantities. I think we're good.
So there was a lot of information given in that problem. So we would want to start with a drawing or a free body diagram of the situation, right, Bhavdeep?
Yep, absolutely. So let's draw a free body. Well, let's draw an extended force diagram and then just draw the triangular situation in which we're seeing a little climber here. We got the rope, we got his body, and we got two angles in the triangle. Actually, that's going to be pretty pivotal in solving this problem. We got the tension going up. We won't draw the components just yet, but we'll try to figure it out later on. We're at a 35-degree angle from the cliff. We got the mass of the climber as well, and we know that he's 1.4 meters from the cliff. Oh, that's our weight. And then we also have a 25-degree angle in there, since that's where he's holding the rope from, if you will. And we have a 1.1 meters from the center of mass of our little climber here. Now we know that well, we have a 25-degree angle inside, and we have a 35-degree angle outside at the base. So inside the triangle, right next to the 35, we know that 35 plus x in that case would be 90 degrees. So basically, the other angle inside the triangle, other than 25, would be 90 minus 35, about 55 degrees. And using a triangle's property, that is that all angles can sum up to be 180. We can conclude that the last angle in our little triangle here would be 100 degrees. This will be important as we start solving for the answer. All right, so as we learned in the previous question, we know that the sum of, well, since this person is in equilibrium, we know that the sum of all forces in the x direction is 0, sum of all forces in the y direction is 0, and the sum of all torques is 0 as well. Just general repeated knowledge, and a pretty standard thing for all equilibrium questions. Now, let's just consider the sum of torques in this situation, and we see that the sine of 100 degrees, what would it be? It would be the vertical the horizontal component of the tension when subtended at 100 degrees, so T sine 100. Times 1.4, which would be the torque at, sorry about that. So torque at 100 degrees. sorry, the tension at 100 degrees would be the torque at 1.4 meters, which is essentially the length of where the climber is holding the thing, minus mg, well, minus the weight or the cosine of the weight, which would be the vertical component of the weight, are kind of counteractive forces when calculating the well, when you look at the free body diagram. If we draw the components real quick, we'll be able to figure out that these things would be counteractive and would be the only two forces um, governing the torque of this guy. Um,
So we have the components of tension here,
right.
and you used T sine of 100 to get the vertical, times its perpendicular distance, which would be 1.4, and we use the weight, and again, its perpendicular distance, which is 1.1, and that is set equal to 0 because the sum of the torques equals 0.
Absolutely.
Which gives T is equal to 525.2 newtons when you plug all of your information in. And again, as a reminder, mass is equal to 82 kilograms for the person.
Right. Thank you for that. Just wanted to make sure that the well, there's a negative sign at the mass spec primarily because these are counteractive forces, which means that one of them will has the potential of taking the climber in a clockwise direction, and the other one has the potential to take him in a counterclockwise direction. According to convention, counterclockwise is positive. That's why we took the vertical component of the tension as positive, and the vertical component of the mass as, or the weight, as negative. And as you said, once we get to solve this, we get a value of 525.2 newtons. Do you have anything to add to that? Would it be cool to move to the next one?
So just to clarify, 525.2 newtons, that is the answer to part A, which was asking for the tension. We did this using the sum of torques equation, which again, similar concept to the last problem, we're just using static equilibrium. Even when there's more information going on in the problem, it essentially breaks down to this. And you can see from the free body diagram that there were only two forces acting on it that would provide a torque, which is why we used two forces. Yeah, I think that's all to add, and we can move on to part B.
Wonderful.
And I will erase some of this so we can have a little bit more space. Okay.
All right. So before we actually begin, or before we actually go on to solving for the vertical and the horizontal components for our tension in this case, the first thing that we need to notice is that 25 degrees is actually the same 25 degrees that we see according to the parallel axis theorem. Right next to our little tension, and well, the angle between the tension and its vertical component would also be 25 degrees because of a parallel axis theorem. There we go. And now we can begin solving for our vertical and horizontal components. So just according to our old vector stuff, or our old vector conventions, we know that the vertical component is tension times cosine of 25 degrees. And when we solve for that, we get a 476 newtons.
And this is using the tension value that we solved for in the last problem.
Absolutely. Similarly, tension horizontal would be the sine of 25 degrees times the tension, which is 222 newtons. Fun little number there. Alrighty. I mean, this was relatively straightforward. It's just generally testing, I guess, the skills to make sure that you got the right answer and that you can decompose it into its vertical and horizontal components. Nothing major. And I guess we should be able to move on then the third part, which is a more interesting one. In this case, we need to, oh, I'm sorry.
Just a reminder, because I know that looking at the problem was a while ago, part B was asking for the components of the force that we solved for in part A, and part C is asking for static friction.
Absolutely. So we're looking for the coefficient of static friction, and I guess we can begin. Now we know that the sum of all forces in the y direction, in this case, would be 0. Sum of all forces in the x direction would also be 0, but then again, there aren't a lot of forces that can really help us calculate the friction, since the friction would be in the y direction. Now, we can say that since this is 0, we can think of all the forces that are acting in the y direction, or from our free body diagram, we can conclude that the force of friction, which would be upwards, minus, so considering that upwards is positive, minus everything that's downwards, which would be the weight, which would be mg. Also minus the cosine or the vertical component of the tension, which would be t cosine 25. I'm sorry.
So in this problem, wouldn't t be pointing upwards?
T would be pointing upwards, as my bad. As we can see from the thing, from the free body diagram, T is pointing upwards.
So that's important to make sure you keep track of your convention, as it'll change the value of your forces, and this should all be equal to 0.
Absolutely. So now rearranging, we can figure out an equation for the force of friction, which is, well, yeah, we can rearrange this to say mg minus t cosine 25. All right, now when we leave it at that, we also see that the force of friction is equal to, according to chapter, I guess 4 or 5 it was, that the force of friction is equal to the coefficient of static friction, which is what we need to find, times the normal force. And the normal force in this case would be the force that the cliff applies to the climber, which would be equal to the sine of 25 degrees or times the tension, or the horizontal component of the tension, since that is the only force that is in the x direction minus our normal force.
And we essentially get that from the fact that the sum of the forces in the x direction is going to be equal to 0.
Absolutely.
And we use our reasoning in order to kind of almost skip that step, because as long as you understand that they're the only forces acting in the x direction, you can automatically say the normal force is equal to that one force, which is the t sine of 25.
And now that we have this, we can just plug that into our equation that we just figured out. So we can say mu s is t sine 25 equals mg minus t cosine 25.
Right. So I'm gonna keep working up here. We get mu s t sine 25 is equal to mg minus t cosine 25. And again, we have all of these values except for mu of s.
Absolutely. And when we found out the mu s, we figured out that it's about 1.48. And since it's a coefficient, we do not particularly need a unit for it, and we should be fine. Did you have anything to add to that, Freya?
Only to point out, you can kind of see this process here of just choosing the static equilibrium equation that applies most and will leave you with no unknown variables. Torque is usually a good place to start, and then you move on to sum of forces in the x, sum of forces in the y. And you'll kind of see that when you take that logical pathway, you'll end up with just one variable which is unknown, and you can solve for it.
Absolutely, that's a great point. And just to kind of reinforce the idea, yeah, take care of your sign conventions as well, as I mentioned in the previous one. I messed up on this one, so we're just totally going to ignore that, but don't ignore it in your exams. And Yeah, that's right about it. That pretty much concludes this question.
Okay, so this one a little simpler, a few less variables, but still applying a lot of the important concepts. So given the radius of the Earth and the mass of the Earth, which are both understandably high numbers, calculate the angular momentum of the Earth. So that's not a lot of information, it's just radius and mass. But with our angular momentum equations that we'll be going over, we'll be able to solve for this. So I will move this over to the whiteboard so we can get started. Okay, so we have the Earth, which is a sphere with a radius of r, and that is a terrible circle, but I'm just going to go with it. So r equals 3.761 times 10 to the 6th meters per second. And the mass is equal to 5.972 times 10 to the 24th kilograms. And we are solving for angular momentum, which is L. And before we even get started on solving this problem, Bhavdeep, what are we expecting for the answer? Is it going to be a small number or a large number?
It's probably going to be a giant number. I mean, it's the Earth at the end of the day. We have two really giant figures with us, so I'm assuming that we're going to get a large number.
Exactly. So it might seem like a small thing to know that, but if you get to the end of the problem and you get some small number, you know that maybe there is a mistake somewhere in the math. So keeping it in mind that the Earth is a large round object, we know that it's going to have a large angular momentum. So the first thing I want to do here is try and figure out which equations I want to use. So I know that angular momentum is equal to I omega. And the reason I picked this one is because I know the shape of the object, which gives me a pretty good indication of what I is going to be equal to, because my moment of inertia is based on shape. And it may seem as if I have no information about omega, but what do I know about the Earth? How many revolutions does it make per day? Yeah, so the Earth, as we know, makes 1 revolution per day. So even though it seems as if you're not given any information, you actually are given a lot of information about the value of omega. So I do want to take that revolutions per day and convert it to something I can use, which is radians per second. So 1 revolution per day. And I know that there are 2 pi radians per 1 revolution. And in 1 day, there are 24 hours. And in 1 hour, there are 3,600 seconds. Now, I don't know the amount of seconds in a day, so I took an extra step there, but if you do know the number of seconds in a day, that makes it even shorter to convert. So 7.27 times 10 to the negative 5th radians per second. That is my value of omega, which just leaves me with I left to solve. So my moment of inertia is going to be the moment of inertia of a sphere, which I can get from the moment of inertia chart, and it gives me 2/5 mr squared. So from here, Bhavdeep, am I able to solve, or am I missing any information?
Well, we got our radius, we got our mass, we got angular momentum. We should be good. We should be fine. Just plug it into the formula, I believe, and we should be fine.
Exactly. So plugging everything in, I get 2/5 mr squared times omega, which is 2/5 times my 5.972 times 10 to the 24th kilograms. And as I can see, all of my units are in kilograms or meters or seconds. So I don't need to do any more converting here, but I would want to make sure that that is consistent. And then I've got 3.761 times 10 to the 6th meters per second. Sorry, I wrote that in meters per second, but radius is in meters squared. And this is all multiplied by omega, which is our value here. So we're going to multiply that in, so times omega. And plugging this into a calculator, we get 2.46 times 10 to the 33rd kilograms times meter squared per second. And that is our final answer. So even though you're given very little information in this problem, with the information that you can reason based on the fact that you know things about the Earth, based on conversions and our moment of inertia chart, and just understanding which equations to use, you're able to actually get a lot of information about the Earth just from very little information about its properties. And as you can see, it is in fact a very high number, which gives me a good indication that I solved correctly. Bhavdeep, do you have anything to add to this?
Yeah, just to make sure that we kind of assume what we're looking for. As we did at the very beginning, we discussed about how big the answer would be. And well, we got a huge answer. So just kind of making sure as to what we're looking for. And if we got something around the order of 2.46 times 10 to the negative 5, for example, that's when we kind of have a problem. Otherwise, I think, I mean, just making something out of very little information is standard normal. It's okay, cool. It's nice.
Okay.
It's expected out of a physics student. That's what I'm trying to say.
Yes, definitely an important skill when you're doing physics is kind of learning to understand that with very little information and a little bit of reasoning, you can usually get to your answer, so long as you have a good understanding of the equations you need to use.
Alrighty, so in this one, this is also a giant question as it happens. A lot of information again. So it's basically an application of torque. I just wanted to go over something that we already covered and just kind of reiterate it, since we're using a lot of torque in our equilibrium and other things that we might cover. So we have a large 16 kilogram roll of paper with radius 18 centimeter. It rests against the wall and is held again in place by a bracket attached to a rod at the center of the roll. Think toilet paper, honestly. The rod turns without friction in the bracket, and the moment of inertia of the paper and the rod about the axis is 0.260. So that also gives you a hint. So we're using moment of inertia in this case. We also know that there is a bracket that makes an angle of, well, I mean, the bracket makes an angle of 30 degrees with the wall, and the weight of the bracket is negligible. So very light toilet paper as it happens. And then we also have the coefficient of kinetic friction for the wall, well, between the paper and the wall. And we have our vertical force as 60 newtons. So think on pulling on the toilet paper, I guess. I mean, if you're really into that at this point. And then we basically need to find the magnitude of the force that the rod exerts on the paper as it unrolls and the angular acceleration of the roll. So yeah, pretty practical, isn't it? Pretty practical example of toilet paper. And if there aren't any questions, then let's begin solving. All right, so the first thing we're going to do is just generally draw an extended force / free body diagram. We know that there is a force along our little kind of bracket that's pulling on the roll. I keep forgetting it, but yeah, never mind. I'll remember at some point. And then we have a normal force that the wall is applying on the roll, and then we're going to put it at the center. We also have the mass or the weight of the roll, and we have a force that is pulling the roll down. We also have the frictional force that is, well, messing with the force in this case, or stopping the force from occurring. the radius is about 0.18, and we also have the moment of inertia to be 0.260 kilogram meters squared. Just writing out a generally given quantities, we also have our coefficient of kinetic friction at 0.25, and as mentioned previously, our frictional force. And we also have, or we can technically decompose this force that the kind of bracket is applying on our roll into its vertical and horizontal component. Since we already have the 30-degree angle, it'll be better to do it just to standardize the axes a little bit.
So again, using our trig rules, using the angles we have, we are able to say that the horizontal one is f sine of 30 and the vertical is f cosine of 30.
Absolutely. And now let's start solving for our force that the bracket applies on the roll, basically. So the F in this case. Now, before we do that, actually, let's assume that this thing is in equilibrium. That is, it's not moving and nothing technically is happening. And we can also conclude from our previous multiple questions that the sum of all forces in the x direction and the sum of all forces in the y direction will be 0. And the torque is 0 as well. Absolutely. So let's consider our forces in the x direction first. We have our, considering that stuff on the right is positive, we have n minus f sine theta equals 0. And this doesn't necessarily matter since we're just gonna rearrange this equation and say that they're equal.
And why do we want to know this, Bhavdeep?
We're gonna know this primarily because we're gonna use it in the next one. Surprise, if you will. But when we actually consider our force in the y direction, we see that we have our, well, considering upwards to be positive, at least in this case, we've got f cosine of 30 minus the weight minus our pulling force, which is 60 newtons, minus our frictional force, and that's a hint as to why we found out the normal force, is equal to 0. So we can also rearrange this equation, try to figure out an equation for our f in the first place. So f cosine of 30 would be equal to mg plus 60 plus f.
And we know that we can convert that frictional value to something else, right? We can use
Absolutely.
our normal force.
So that's kind of why we found out the normal force. We haven't been given the frictional force, but we've been given the coefficient of kinetic friction, and we found out the normal force, and now we can just put that in. Now, just substituting for the normal force, we know that it's f sine of 20 or 30 degrees, and now I believe we have all quantities. So, do you think there is another step required, Freya, or do you think we can solve for f eventually?
I think we can solve for F because we are given all this information. We have the mass, we have gravity, it's a constant. We have mu of k, and we have the angle of 30 degrees, which is just leaving us with F in the problem. I think the only thing here is just to be very careful about factoring out the F and making sure we solve correctly as it is, as F is in two parts of this problem.
Absolutely, absolutely. So when we do factor out the f, we get f is equal to weight plus force, or 60 newtons, over cosine of 30 plus mu k of sine 30. And that's where the factoring out kind of comes in. The first time I solved this problem, I messed up on the mu k, and that caused a whole bunch of trouble for me. But just making sure that everything is in its place. Basic algebra at times is something that everybody messes up on. And once we solve for all these given quantities, we get an answer of approximately 293 newtons. The answer will vary around 292.8, but we're just going to take 293 for the sake of ease. And that's our first part. Did you have anything to add to that, Freya?
No, I think that this covered it. As you can see in this problem, which is a little different than the last few ones we've done, rather than starting with torque, we started with a sum of forces in the x and then went to sum of forces in the y. So as you can see, you don't always have to start with torque. It might happen a lot, but generally you just want to pick the equation that best fits the problem that you're trying to solve for.
Absolutely, certainly. And now I believe we can move on to our second part, which is the angular acceleration of the roll.
Okay, so again, just a general drawing here to keep it simple. We have the 60 newtons, we have mg from the middle, we have normal force, we have frictional force, and we have the components of the pulling force, the bracket.
Absolutely. Well,
Sorry, let me switch that around. It's F sine of 30 and F cosine 30. Okay, it's just a good idea to keep track of this information as you're working through the problem, as these forces will come up again.
alrighty. So in this case, now is where we kind of use our torque. So let's assume that we're out of equilibrium. We're pulling on that thing with a force of 60 newtons. So it has a torque which is non-negative, and well, the sum of all forces doesn't really bother us in this case. So we know for a fact that since we need to find out the actual angular acceleration, and we've been given the moment of inertia, we can use a formula that says the sum of all torques is equal to I alpha, in which case alpha is the angular acceleration and I is the moment of inertia. Another formula for torque is the force times the radius. Or the sum of all torques would generally just be the sum of all torques. So the sum of all force times the radius. So we can say that considering say clockwise to be positive and counterclockwise to be negative, that it would be F minus F, which is small f minus big F times R.
So our frictional minus our pulling force, F times our radius.
Absolutely. And now that we have these, we can kind of equate them to find out an equation for our alpha. However, before we do that, just to make sure, we need to kind of find out the frictional force again, because we didn't figure it out in the last. I mean, we figured it out in the last one, but we don't have an independent quantity for it. So it will be good to figure it out first. We know that F is equal to mu Kn, is equal to mu Kf times sine of 30, and we do that thing again, which is annoying at this point, but sure, we'll take it.
And Bhavdeep, just to check, so your torque equation, the reason you were able to identify that these two forces were acting on it is because all of the other forces act along the axis of the circle, right? Leaving only two forces that would apply torque.
Absolutely. Only these two forces are being applied around the circumference of the circle, so they will necessarily impact where the circle moves at the end of the day.
Okay, so this big F here is our 60 Newton force, just to clarify, as there are a lot of forces acting on this object.
Alrighty, and then we have an equation for our frictional force, or at least we have an expression for it. and that is mu k f sine theta, or 30. And since we know f, we can figure that out, and we'll get a final value of about 36.63 newtons. Oh, is it that value is just for the frictional force?
Oh, you're looking at this. Okay. Yeah. So you said 30.63?
36.63.
36.63. So plugging in the value of f that we got from the previous answer and using our mu k value and sine of 30, we get 36.63 newtons minus 60 newtons times our radius, which is 0.18 meters, is equal to our I alpha.
Alrighty, and then we can figure out an expression for alpha where we just basically divide both sides by I and try to figure out what the answer for the, well, try to figure out what we get for alpha.
And I, in this case, we were given in the problem, and it was equal to 0.260 kilograms times meter squared. So we are just left with the value of alpha as our only unknown. So using algebra, dividing, we end up with an alpha value of 16.2 radians per second squared.
And that is the answer. And that kind of wraps up the entire question as well. This had two parts. Fred, did you have anything to add to that?
No. So as you can see, again, pretty much every problem here, you can see how it's come back to our equilibrium equations. In this case, part of the object could be considered an equilibrium as it was not moving in the x or y direction. However, its torque could not be considered an equilibrium as it is rolling, it is moving. But given the information we have, given our understanding of the equations, we are able to reach our final answer. So again, knowing how to use those equations, whether they're equal to 0 or not, is very important.
Certainly, that's a great point. And if there are no questions from anybody, we, I believe, can move on to either the next problem or more questions if anybody has any.
So if anybody has any questions about this problem specifically, feel free to ask. Otherwise, we'll move on to just general questions if you have any.